Okay.
All right. Thank you very much. I hope this still works. Yeah. Just a quick update. Last week, I think I said something wrong. I said something along the lines of there could be a way of doing probability theory with using negative numbers from minus infinity to plus infinity. I don't think that's true. I think it still has to be a positive number, just as an erratum. Yeah. What are we talking about today is expectation propagation. The problem setting is quite similar to last week, but maybe slightly more specific as an application to probability theory, namely the very common case in data science. We have data, we have parameters or a model that we think should generate this data, and we ask what is the distribution of those parameters that best fits the data. If you think about this, is pretty much what all machine learning or all data science tries to do in one way or another. We also want to know not just what the distribution is, but also how much evidence a particular model class gives us, because that is necessary for us to then decide which one of those possible model classes is the one that actually fits the underlying process. So we can use this to explore a bit based on the data, what is the most likely scenario in terms of generating process. So science. Oops, we have the issue of 1 second. Right now, much of the paper actually talks about the toy example, namely where we have a data process that spits out numbers y, and is essentially the parameter that is being spit out is x, which is exactly the same as y hypothetically. So in principle, if you to measure y often enough, you should get x back. The issue now is though that in this very clean example, we add noise, essentially a second process that with a probability w generates also valid looking y's, but they are in a much wider distribution. And if you remember last week, we quickly talked about the Kalman filter, which made heavily use of everything being Gaussian, all the update rules and everything, which breaks the moment we have like sums of Gaussian. So essentially this is like an example of a system that is simple, yet already complicated enough that a lot of stuff will become intractable. So we can control the noise levels, and we assume that the x beforehand is an even wider prior. So essentially, any noise we measure should definitely be still within our prior, but that should hardly matter for practical reasons, I think. And so what is our best guess at a distribution of x given these measurements where we have a chance for any measurement being essentially just pure noise without any signal to it whatsoever? Why is it important? Well, yeah, we talked about last time. We can often decompose these problems into graphs with message passing, and typically,
Sorry,
well,
can I
these are
ask a
functions.
question, Connor?
Yeah, please.
So what do you have variance 10 and then 100?
Say that again.
You have variance 10 and there you've got 100.
Yeah, these are, I think, just toy numbers. I mean, they could be anything. I think that the point is here that your measurement noise is essentially 1, right? Or it's a matrix, but the diagonal of the measurement noise is 1. The variance of your noisy process that is overlaid has variance 10, essentially that any measurement would is if that was the other way around, I think then you would never be able to actually get any true signal out, probably. And the prior is that essentially the prior could be any function that is seemingly broad, so that our noise and signal is somewhere encompassed. Right? We never want to be in a region where the prior essentially says there's a 0 chance that the true signal isn't there, but then the true signal isn't there. But it technically doesn't have to be. The prior doesn't even have to be normalized, I think, in most applications, but here this is just bigger. Does that answer the question?
Sorry, I'm not quite sure what you mean by sort of wider prior.
Wide as in spread out, right? The uncertainty of X.
Oh, the larger variance, do you mean?
Yes, yes,
Oh,
yes.
okay.
Sorry, that was me
Yeah,
being
sorry,
a bit flippant with my language. Yeah, so we talked last time about message passing, that messages being passed from different nodes to each other. And in the discrete case, these essentially are dictionaries with values that can be updated. In continuous basis, these become functions, and generally integrating over functions is a bit difficult, and integrating over function can make the family of functions change, or maybe essentially can create intractable distributions which are not easily being worked with. And so the question is, how can we find a system that can actually deal with these more complicated real world scenarios? Now, for this particular problem, right, it's, of having these n measurements all being essentially the same, we can just apply what is essentially Bayes' theorem, or the rules of probability theory to factor out the combined or the joint distribution into the product of the prior and each individual measurement being one signal, and they are all independent, right? And we can even treat the prior itself, because we chose it to be Gaussian, to be just another of these factors, right? And if you think about what the graph looks like, essentially we have n factors all passing into the same variable, and the variable is a vector rather than a single number. But it's a very simple graph already, right? However, because of this sum, or each term being a sum of Gaussians, the product itself becomes also, a product of the sums of Gaussians. So the whole thing becomes already not very nicely described by very few parameters, at least not naturally. And the idea of assumed density filtering, which is actually a method that predates that particular paper, is to just assume that whatever the outcome is, it's should be Gaussian. And so we try to, or they try to find what is the best Gaussian approximation to the product of these factors, right? So the factors, each one is not Gaussian, but you think of this, if you multiply them all together, they probably are something that sort of behaves like a Gaussian. So what is the best approximation of that? And how do you go about? And this is, again, still an old paper. You start with essentially a flat prior, and then use update rules, right? So we know what our so for each new factor we want to take into account, we know what our prior distribution of X is before we have taken that new factor into account, and we can get the exact prior by taking our new factor, multiplying it with the previous prior, which we say is Gaussian, and calculate that. Now that thing, because again, because T is not Gaussian, this thing becomes ugly. So what ADF tries to do is to find what is the best Gaussian approximation of this posterior, and basically does it by minimizing the KL divergence between the class of allowed functions, which are Gaussians, and that particular factor. And that is being done because Gaussians are essentially described by two exponents, right? The mean and the variance, or standard deviation, or whatever system you choose. And so the best match is the one that matches on those momenta of the distribution, and that leads to update algorithms. So for this particular case, these
Arvid,
yeah.
quick question. T over here is a distribution over each of the observations or like data points you have in your data set?
Yes. So it's T is the factor given X let me see. This is essentially t, right? So it's given an x. It could be either it is actual signal, this part, and then it should be the y is observed, right? So this gets a likelihood, but at the same time we also have the option of it being just noise, and then we get a little bit of probability just from it being from a fairly flat distribution.
Mm.
And that's the problem, right? If we were to just multiply this with a Gaussian, it's not a Gaussian anymore. And so this assumed density filtering is sort of making the case. We take whatever is our posterior here, which is not Gaussian, but by matching the posterior moments with the well, by calculating the first and second moment of this distribution, we can easily find what is the Gaussian that best fits those, and that is namely the one that has exactly the same moments. And because this integration is actually doable, this leads to an algorithm. Namely, we initialize our total Gaussian by our prior, aka we say it's mean 0, it has the 100 width and the scaling factor S1, which is sort of a factor that does the compensation constant. Whenever we update it, when you plug in the numbers, it turns out this number becomes quite useful, which is 1 minus 1 over z w n, or the Gaussian density of the observation for the white noise signal. And if you think about it a little bit, this is actually the probability of the signal being, or that the probability of your observation being actually signal. And then if you look at it, the mean after the new observation is essentially the old mean plus the term that is proportional to the probability, right? So if I'm very certain that my observation actually is outside the noise realm, I'm gonna give it a lot more weight rather than if I'm less certain about it. Here we still have the ratios of the variances of my prior belief, and here it's annoyingly is the factor of 1, but that actually is sort of the measurement noise. So if we were to change the problem setting ever so slightly and would say that the measurement becomes more noisy, then also do less updating. So that is actually the old Kalman filter update. The only difference really is this probability of saying, yes, this measurement is actually a true measurement rather than noise. And similarly, we get for the variance update that each measurement, if the measurement noise, if the measurement is almost certainly signal, and we actually reduce the variance, right? Because we increase the precision of our estimate. However, we also add noise by not being sure whether the new measurement was actually true measurement or whether it was just a random noise. You see this r times 1 minus r is, I think, the variance of the binomial distribution. So we get this new noise injected just by the fact that this is a mixture of distribution. Sorry, the other questions? Yeah.
Sorry, I was wondering what's S?
S is a normalization factor. Essentially, it's I think it follows out from the I think your standard Gaussian normalization factor is something like square root of 2 pi. I think yeah, something like that, right? And I think this S is like sort of a factor that yeah moves it away from that essentially. But I think it shows it to be starting from 1, so that z is z0, and then just updates to that to make it slightly easier to follow, I think.
And Z and Zi?
Zi, I think, is the overall normalization constant of the resultant Gaussian, yeah.
That's Cartesian product of two normalization factors. Cartesian product.
What do you mean by Cartesian product here? No, I think this is just a scalar product here, right? Both are scalars, so it's not. I know, I think it's not a cross product or any vector product.
Can I ask you about TI? Is that just a different notation? I didn't quite.
TI.
Yeah.
If you go back,
Is that just for, yeah.
It's literally just the factor, the observation factor itself, but it could also be the prior term is also treated as a TI with a slightly different structure, right? But it's generally just any factor that is in our updates, as part of our updates, we call TI here.
So TI, where I is 0 is P of X, and TI with I is 1 is P of Y1 gives X.
Yes, that is fair to say, yeah. I mean, the order clearly doesn't matter, right? Or what one would think, at least, that yeah, because the products, you can just always rearrange them, yeah. Yeah.
Arvid, based on what the formulas we were seeing in that slide, the last one we were on, does the model does this method make the assumption that there's like a clear signal plus some noise term?
Yes. So these equations are a direct result of our toy model being exactly that, the sum of the true Gaussian and the Gaussian with the noise variance that is centered at 0.
Okay.
So if you were to apply this to a different factor structure, you would get different updates. And in fact, we're actually going to see this later, though I didn't bother to write down the update rules, because usually it's hard to parse on a look at it. Anyways, here it becomes kind of straightforward because of this nice interpretation of Ri being the probability of your problem being actually signal, or your measurement being signal, and then you just have a standard noise weighted update to your means, which is your Kalman filter essentially. Again, it's more about the formulation itself rather than the particular set of rules that come out in this particular instance, to be honest. This is still these old assumed density filtering. So that was the first approach that actually came before this paper. And what is a bit annoying with this solution, right? So you start at your prior, and then you update it until all of the points have been looked at once. And when you do that, you realize that the actual order in which you look at these points matters, right? And we started out from a product of factors, so where the order clearly does matter, because products just flip around. But here, actually, the order in which you look at the points matter, because the way the prior updates and then you look at it makes a difference. And you can't easily just say, oh, then why don't you just go over it again? Because then you would essentially be double counting observations. You get your whole you get false precisions, all of these kind of things, which clearly is also wrong. So that is what this paper tries to sort of sort. And how does it go about? And it says, well, if in the previous solution we had, after every step we have an update, we get a new mean and a new variance and this the scaling factor. And rather than saying this is like the iterative solution itself, we say that is our current best guess at what the global solution is, right? So we say that global solution, the product of all the factors, is essentially Gaussian. And so this is our best guess at that. And instead of saying like what was the prior before we looked at a particular point, we sort of rephrase it and say, what is the prior if we look at the whole problem itself and just take this particular point out, right? And by doing that, the order itself doesn't matter, because all the other points are technically still in there. And we still want the global solution to be an exact solution, in the sense that the global solution is still Gaussian, and rather than that being actually the approximation, we say that actually we try to find a problem that fits as closely as possible to the original problem that allows us to exactly solve it. This is, I think, quite neat. And doing that, the idea is that all of these factors, which before were these sums of Gaussians, which sort of are messy to deal with, are approximated by actual Gaussians. And the idea is also then to iterate over those to get better and better approximation of those Gaussians to get essentially a better approximation of your problem, and then you have the exact solution for it. Let's try. So each point can be multiple times iterated over, right? Because rather than going iteratively, we just say at any point in time, we take our solution and we sort of factor out how the solution would look like if we ignore this particular point. And this works here well because our global solution is Gaussian. Each particular approximation is Gaussian. So if you just want to take it out, we can essentially divide by it or remove the component of that particular measurement in the Gaussian exponent. And so we can at any point in time just say, how would my solution look like if I ignore that point? And okay, this is again iterative convergence, and at each point we calculate what is the correct distribution, the approximate solution to at each point. So at each point we iterate over, we can sort of ignore that one point, get the prior that is the best approximation given we have seen everything else, minus that one point, measure, update our total posterior using the similar rules as they were used before, is essentially using momentum matching, and then iterating that out again. And once we have done that, so one at the very end, say imagine we do this long enough and everything has converged, we can get the exact solution again as simply as the product of the Gaussians, of the Gaussian approximation of each of our factors. And from that, it's also fairly straightforward to calculate the evidence because it's the product of Gaussians, which is naturally easier to integrate over.
Sorry, can I ask you a question about notation?
Please do, but don't expect too much.
Sorry, I was just wondering if that /I. I haven't seen that one before.
Yeah, this is actually a fairly common, common notation in these say I think often appears in the combinatorial problems when you want to say everything except that one point. So Q \I is our full Q, so our full prior, which is actually already our final solution, minus that one point, aka so here is actually an index missing. It should be Q, total Q divided by the Gaussian approximation of factor I. That would be our best guess at our prior, provided we ignore that particular point. Yeah. So yeah, and so we say that each factor itself is supposed to be approximately a Gaussian. That means that if we want to actually do this, if we want to continuously update all of these factors as Gaussians, we sort of have to add a little bit more memory, right? Now every factor sort of has to keep track of what his current or its current mean and variance and scale factor is. So one way so that is like a side effect of this algorithm is that we have to add a little bit memory to the algorithm rather than the assumed density filtering, which would just go through and you would only ever update our total number. So this is slightly different. It can be initialized. So in each loop, this is exactly the step that is happening when we remove the observation I from our prior, right? So we remove the precision, we roll back our means, and we roll back by as much as we think this particular point adds its noisiness. So it's all noise adjusted. The actual update step is exactly the same as in ADF, because that is just these momentum matching. There's also the step that technically would be different if you have a different problem where you don't have just a sum of Gaussians, but rather some other function. And once you do that, you have your update step, so you know what your best guess at the posterior Gaussian is, and you know what your prior Gaussian was before seeing that point, so that your best guess at what this particular point added is again just the Gaussian combination of the two. Like posterior minus prior is exactly the Gaussian contribution that this particular point gave to your problem. And again, if you do the math, you see that these S factors update in this particular way. Again, if you once you have that, you can calculate the evidence, which is essentially your the distance vector or noise weight or uncertainty weighted distance vector of your global solution minus the sum of the distance vectors of your squares of each contribution. So the closer they are in value, the more similar they are. So you could argue that intuitively means that your true global solution is closer to your solution in space of these measurements. Yeah, and that is then where this evidence term comes out, and so it becomes essentially exactly solvable, given you approximate the problem well to begin with. That was a lot. Did it roughly make sense? That we turned essentially an iterative solution into something that can be looped over indefinitely, hopefully converges, and at any point in time we essentially can go back to any factor, take out whatever contribution this particular factor gave, and compare whether this moment matching still works well enough, or whether essentially a correction to it has to be done that slowly updates each approximation for each factor.
So a couple of questions. One is, convergence is when you take out a factor and there's no change in the other parameters that you're estimating. Is that true?
Yes,
or no?
essentially that's right. So that you take the factor out. So your factor essentially has a mean contribution and the noise contribution, right? So you take your factor out, you look at what is the prior, what is the original factor to begin with, and if you then do the moment matching, the result that you took out should be very, very similar to the result of the moment matching. And once these become very, very similar, then your system has essentially converged.
Okay, that makes sense. And you said right at the end of the explanation of this slide that one thing that matters is, I guess, your prior, or what that you start with, or what do you have to estimate well in order for this to converge?
Well, ideally, the Gaussian approximation of each factor should look very similar to that factor, I would think, right? So that yeah, essentially, I don't know whether that is necessarily a great criterion by itself. I've seen a little while that typically the more points you add, the more similar your global solution is actually to a Gaussian, so the better your approximation gets. So that is actually one of the nice things about this solution. It tends to work better on larger systems. Naturally, if your factors are very, very asymmetric, so that like say you have two modes that are very, very far spread, then you could think that your higher order moments are not close to zero, and then you would expect your distribution approximation to be worse, just because yeah, your Gaussian approximation at each step is worse. But then again, if you have many of them together, and I think that is the consequence of your law of large numbers, right? The higher order moments, like the cumulants of those should essentially go to zero, the more factors you have, right, and the more factors, essentially, and you say each factor has like a cumulant that could be a third order cumulant, I think they're called, that is like positive or negative, more or less randomly. The more of them you add together, the chances essentially grow that your overall solution has smaller and smaller higher order terms, because they did essentially have a good chance of canceling out, especially during this calibration process, that your overall solution becomes more and more accurate as you would increase the problem. You could easily think, right? So if you have this toy problem of, if you only have one measurement, right, and there's like a 50% chance that this is actual noise, then the one measurement won't tell you much. But if you have like 10,000 of them, the combined weight of those probably makes your measurement noise a lot less likely to be mattering, really. Yeah, I don't know whether that is a really satisfying answer or not.
It
Yeah.
helped.
It just interesting that this algorithm seems to be converging always to a stable point, and I think he argues in the paper why that is, because it's of this exponential function family. But that stable point doesn't have to be unique, I think, and it doesn't have to be necessarily the best solution there is. Now he ran actually tests on this particular toy problem of this Gaussian mixture, and we see EP is expectation propagation, so that is this mechanism versus others. So we have Laplace and variational Bayes, which are fairly common other methods that approximate densities. And we have importance sampling. Now, importance sampling tends to be slower, right, because it samples, but it tends to be also better at finding at dealing with the issue of having distributions that are non-monomodal, like Gaussians, but rather could have two different peaks. And generally, you see, if you look at, say, in the case of 20, so very few measurements, or 200, that the expectation propagation converges rather fast and gives you a fairly good trade-off between speed and the solution being found being good. You probably also see that, especially for lower number of points. So that is the issue, that the lower the number of points, the more structure your solution actually has that is different from it being Gaussian. Eventually, even though it's expensive to do, the importance sampling will find solutions that are probably better, as over here. But as the number of observations or factors really scales up, that is not being true anymore, right? So then you could also imagine that the more factors you get, I think there's more chance for this importance sampling to get sort of stuck somewhere, and you get not necessarily a better solution. The posterior mean, though, is a slightly different matter, right? Because there you would expect, so this is like the mean of the final distribution compared to the mean of the exact final distribution, and their expectation propagation still converges fast and typically finds a good solution. But also, again, the importance sampling can better find those modes that are not maybe the maximum mode, but still contribute to your probability. I think, yeah, it's here, it's visible. So this could be like a problem where the sampling or importance sampling is quite good, right? So your expectation propagation essentially finds the maximum peak here, and that is your solution. It's a good solution, so the evidence might be low. However, if you want to calculate the mean of that distribution, you would set it essentially to the mean of the mode, whereas importance sampling will occasionally end up in this peak, and so your true mean is probably shifted somewhere. So that's why importance sampling can, for these small problems, give has a good chance of giving better solutions. But again, this is a very, very, very small problem of essentially, I think, only 2 or 3 factors. The moment it becomes larger, importance sampling really slows down, and EP is pretty good again. There's one more generalization, right? So we talked about how this toy problem was essentially a product of identical factors. For graph applications, there's actually no real reasons why these factors all have to be the same. Right? Quite generally, if I have a model where I've observed nodes, unobserved nodes, so you know, a model of hidden parameters essentially, and observations, I can always write them into this product form. Each term potentially can be quite nasty in terms of what the law of distribution is that it creates this. This algorithm should still work because you know the factors can be interpreted again as the messages that are being passed between parents and children, and by having many of them and optimizing iteratively over the whole thing, it typically does converge. And he says if it doesn't converge well, it's probably not a well-chosen model. And the solution just works because you at any point in time you work with Gaussians. If a factor only depends on a subset of all the variables that you're actually looking at, it's very easy to ignore the parts of a Gaussian that, because the Gaussians are diagonal, to ignore the ones that are not important and sort of marginalize over them, and still you can calculate these approximate messages, and everything essentially still works. And that's why this EP algorithm also does work on these larger networks of probability graphs, which is quite handy for ever so slightly bigger problems that are maybe still not massive, but already bigger. And it's also nice that you know that typically you will find a stable solution in which everything is in equilibration. It might not be the best, but it should be there. One particular example he gives is also quite useful. Is the base point machine. It's essentially a model where your data is binary. So the outcome is either plus or minus 1. So it could be like observation of some sort. And the model is a I forgot what this function is called. Essentially, the integral of the Gaussian up to a point is the link function, essentially saying that your W is what would be your weight matrix in a typical regression problem, and the more the weight matrix aligns, or the weight matrix essentially takes your input vector x, rotates in one direction, and along that direction is like, or along this direction is like an ideal direction. The further along this line, it makes y either being very strongly in being plus 1 or minus 1, somewhere along the middle, where this wx is fairly small. This smallness is described by this epsilon parameter. There's a chance for y to be plus or minus 1 because this function is essentially 0. Not 0, but 50%. And so this is quite similar to the clutter problem, that namely that they have these n factors and they are non-Gaussian. So all the things that works is just that the update equations themselves are slightly different. They are in the paper. I don't think that they're really that interesting to look at, but your mileage may vary. I mean, you look at the solution. So he compares it, and it's a bit of an older paper, to the SVM. What does SVM stand for? Like this kernel machine.
Support vector machine.
And there we go. So out of the box, of course, there's also a bit of tinkering one can do with the support vector machines. It tends to work rather well. So this is like a small point problem. Support vector machine typically tries to optimize the margin, whereas the base would can be interpreted as a sum of all the different distributions of the weight vectors that could be multiplied by the chance of that being the correct weight vector. And if you look at the solution, so EP and Billiard are both base machines, so they give very similar, or base point machine give very similar accuracies. So and they tend to be better than SVM. So they seem to be fitting a lot of these data sets better. But the difference between EP and billiard is that, and I don't know exactly how the billiard algorithm works, but EP converges drastically faster, essentially giving the same or better error in shorter time. And so that shows that this approach seems to be working quite well for this class of problem. That brings me to the end. So yeah, it is an algorithm that can help solving belief networks, at least approximately, or where you have hidden nodes that have that work on continuous variables. You at each point you can calculate efficient update rules depending on what the node structure is that you're trying to approximate, but that still requires actually work. It always converges, but it doesn't have to be the best solution. It has many practical applications. And I think where it gets potentially difficult is when you have factors that are fairly complicated, right? You could imagine that the factor being multimodal, or have some additional structure where it might be difficult to calculate actually update rules that are nice and algebraic that you can just run them over. But I would expect that for these small problems, you might actually get away with using linear, numerical integration, right? So if you have only like very few dimensions you want to integrate over locally, it might become feasible, and then you can still use this EP propagation to essentially use the results of your local integration and spread them out across the whole network and hopefully converge. Yeah. So and it works better the bigger your problems typically are, because the larger the problem set is, the more the natural posteriors already approach something that looks like a Gaussian, and that is also the thing you're trying to approximate them with. So you would expect them, and here shown also in some of the toy models, that for larger problems this gives better solutions than for smaller problems. That's pretty much it. Any questions? Or what are your questions? You must have questions.
Thanks, Arvid. So like, one of my questions is, so do you find this method of approximate inference quite restricted in terms of the model that you can propose in the first place? Because you have to write down.
Yeah. Well, it depends.
You have to write down what the model is in terms of the product of densities, and that means you need to write down what the density is. So you have to assume a probability distribution form for each of those densities. And increasingly in machine learning, we can't even write down a density because we're not trying to model something as Gaussian. But what I will say is that this method of approximate inference is good for kind of these types of problems where you can write down a model that's useful like that, such as if you've got a league of tennis players and the tennis players each have a skill, and that skill is modeled as a Gaussian distribution. So they have a mean skill, but they're not playing the same level each time, so they've got some variance. Some days they're bad, some days they're good, but around this level. And the factor graph, the edges become like the way you transmit information between players. So like a win or a loss when a player plays another player. And so then each factor in that product distribution is the likelihood that occurs from observing a win or a loss.
Yeah.
And so then if you observe a win or a loss between players, and I think the number of variables are the number of tennis players. And so this is called a true skill algorithm, and it doesn't apply to tennis. It also applies to other sports.
That's great. So that is what I'm gonna talk next week about. So true skill 1 and 2, and true skills for time. But you're absolutely right. So that is one of the nice applications where you can assume, or actually there's a question, can you always assume what is this, whether this distribution actually behaves like this? And then this mechanism becomes actually a way to finding out what might be the right solution, basically because it can help you calculate this evidences of your data set being generated by that mechanism, and you can, in principle, decide which model you have of your tennis players playing against each other being better or not. But yeah, you're absolutely right. I think even for very, very large machine learning models, you would in principle expect that your distribution, if you were to go purely statistical about it, if you were to look at what the weights of those things should be, there probably should be also something Gaussian. Though it's a problem because there's degeneracy in big models. It's hard to say. Yeah, I don't know, but yeah, it has multiple implications, and even practical. If you think about how many points can you if you have to, for each node you want to have at least 3 numbers, right? So your mean of that node, your variance, and the scale factor, that also becomes at some point a limitation once the number of nodes becomes very, very large.
Okay. Yeah. If you go back to the slides on the comparison between the Laplace variational expectation propagation on the multimodal distribution, so the multimodal is presumably like the exact posterior. So you can see the Gaussian assumption, like the Gaussian approximation, is not very good here because it's got 2 modes, and the approximations are all unimodal.
Yes.
So the approximation will only be good if your distribution is 1, it's not skewed heavily, and 2, it's not multimodal. But
yes.
Maybe you don't care about the other mode in this scenario. You just want to denoise it. So you wanted to find that X, which could have been like part of the clutter distribution or part of like the true signal. You just want to find the true signal, so you only care about the highest mode.
Yes, so and you could also exactly as your problem gets actually bigger, very likely the ratio between these 2 nodes will also change, right? So that the maximum node will become bigger and bigger and bigger, and the relative importance of the smaller node becomes smaller and smaller and smaller. And then, even though yes, you won't find this because it has less weight attached to it, it wouldn't really appear much in many post. At least in the posterior means, it wouldn't matter that much. Of course, there might still be other probability outcomes that where that matters a whole lot, right? I think that the best example is always air, right? If you look at air, it's a distribution of many variables, each of them having the highest chance of each. If you look at any molecule in air, the chance of it actually standing still, having no velocity at all, is actually the highest of all probabilistic states. But the matter of fact is you have many of them, and because there's only one way of a molecule essentially can stand still, but there are many ways in which a molecule can float about, even with little energy, that the effective velocity distribution does not peak at 0, but rather at something finite, which means that air actually has a pressure and we can survive, which is great.
Yeah, I kind of agree with that point. And it's the same thing as if you take an image and you sample a random Gaussian white noise and it looks like a broken TV, like it's speckly, it's white noise. But then the most likely would be just pure gray. But none of the images, when you sample randomly, look like that. But then again, that's still a Gaussian example. Yeah. But typically, if you sample an image of a celebrity's face, it's not going to be Gaussian distribution.
Yeah. That is exactly. That is where you're absolutely right. Like data spaces in real world problems like images or I don't know, a language. So it's generally hard to reason really about what does a meaningful probability distribution actually looks on that. I think that is where these stable diffusion also actually quite good at sort of linking something that is a flat, boring Gaussian and sort of pushing it back into a distribution over something that looks real essentially. But yeah.
I really like this slide because it, I think, summarizes the paper quite well. It's a trade-off between how quick the algorithm is, so the number of flops, the lower is better, and the accuracy. Yeah. And you can see that the advantage of expectation propagation is for like a reasonably small computational budget, it's quite good in accuracy for the error, and but the different algorithms boil down to different optimization objectives. So these are like, instead of finding an integration, which how you'd calculate the true kind of posterior. Maybe that integration is not tractable. So instead, you convert it into an optimization problem. And so what Laplace does is you fit the mean around the mode, and then the curvature around the mode becomes your variance. So you can see the dashed line is fitting the curvature to that mode.
Yeah.
Expectation propagation minimizes the KL divergence, which penalizes putting probability mass where there's not meant to be probability mass, but rewards putting probability mass where there is. And VB is the opposite of that. It's like VB penalizes not putting probability mass where there is meant to be probability mass. So you can see that's why VB here, or is it the other way around? VB is like more concentrated around the mode, whereas EP is more spread out, because you'd be penalized for not putting that probability mass where it's smeared out the true distribution. And so it turns out that way around of doing things is a bit more accurate in terms of like the things you're actually interested in. And also EP is like computationally less expensive when you need to do things sequentially. However, I think recent developments in the variational part of the literature have made it easier to do this in parallel. So it's kind of variational methods are still kind of the more popular methods, because EP is kind of restricted some of these models which you can factor out into distributions which you might not be able to write down anymore, and it's sequential in the algorithm. It's iterative, which is hard to parallelize.
That you're absolutely right. Cool. Yeah, I think you're absolutely right. It's also as you said, right? It's your utility function or your loss function. How much do you care? How sensitive is that function to these satellite modes? Yeah, and it might be for some problems that might be exactly what you need. I think in so where I've seen a lot of important sampling being used is in actuarial science. I think where people model like the transfer for very rare events, and that's where these sort of shine, right? Because yes, they are expensive to run, but you at least will occasionally find these very rare instances that potentially could ruin you as a company. So there you definitely don't want to trade off this accuracy for speed or the mode, right?
Yeah, maybe the important something is theoretically maybe exact. I'm not sure, but it just take a long time to propose a sample that you're actually interested in if you don't have the right assumptions.
There's some really interesting papers on, because you essentially can treat them as a sort of Hamiltonian, or like a sort of, I think it's a Hilbert space problem, but with an effective Hamiltonian, and you can show that when there are any kinks in this Hamiltonian, essentially your sampler has a hard time getting around and kind of get stuck in there and can get wrong distribution. At least the convergence can get so slow that in realistic timescales you don't get a good sampling of your space. But there are also ways of getting around that. I think there have been some recent advances in that as well, that sort of make the sampling a lot more efficient. But I haven't read up on the literature at all, mostly because I don't really use it in practice that much. Cool. Any other questions?
Doesn't look like it, but thank you for that presentation, Arvid. As always, very high quality.
Thank you very much.
And learned a lot. So thanks, and we're gonna have part 3 hopefully next week.
Yeah, even though Ben already gave it all away, so what's the point, really?
I'm sorry about that.
No worries, mate.
Still a spoiler for next week. True skill.
Yeah. Is it already in GitHub? I don't know. But yeah.
No, it's not. I'll put it up soon.
Cool. I'll try to make it in time. This week already has been quite busy actually. So, but I just managed to do it. So always keep your other paper in the back just in case.
I will.
Cool.
Yeah. Thanks everyone. Have a good weekend.
Cheers, bye.